Well, welcome to the seventh video that we have. This one is a little mixture of items. If you notice, it's fertilizer labels. What does it mean when you read some number on it? And a little bit about different characteristics of various fertilizers and usage. So it's a relatively short but kind of a mix of things. As usual, we want to make sure that you're aware of the other resources that are available on the ITRC website. And www.itrc.org is the main website. Just remember it's ITRC, not IRTC. That's a thing people get mixed up on, and you can weave yourself around and find videos and books. The other reminder is that we have videos not only of these lectures but also of various labs. Now down to fertilizer labels. First of all, when we talk about fertilizers, at least in the books, we talk about things like potassium nitrate. Farmers often refer to fertilizer in different ways. For example, if you look at the bottom of these words, it says potassium nitrate is labeled as 13-044. And farmers may actually be more familiar with that type of terminology. Anyway, what you have is when you have a fertilizer like potassium nitrate, it will always have these numbers associated with it, and the numbers are related to the concentration of nitrogen, phosphorus, and potassium. But there's a little trick to that because it's not quite the way it seems, and I'll show you here in the next slides. This slide illustrates what I meant by it's not quite the way it seems. Carrying on with the example of potassium nitrate, it's labeled as a 13. That's the N part, the nitrogen. And then 0 is, let's see, it's N, P, and K. So 0 is the the phosphorus, and the 44 is the potassium. Now, going down one step further in the orange, it says the 13-044 means that if you have 100 pounds of fertilizer, that means the fertilizer contains the equivalent of, and then in the green we have three different numbers. The 13 is for the pounds of nitrogen per 100 pounds of fertilizer. In other words, it may not be, well, it may be urea, it may be ammonium, it may be a mix of urea ammonium nitrate, but expressed as N nitrogen, in 100 pounds of that fertilizer, you would have 13 pounds of N. The 0 then, moving down, is P2O5. It's not P and it's not phosphate. And so here's a kind of a new term, this P2O5. That's used in the fertilizer rating. And then you have the number 44, and that refers again to a kind of strange thing. It's K2O. In other words, it's not 44 pounds of potassium, but it's K2O. So then you can have conversion tables to move from these values to something. In a previous video, you were given the equivalents, or actually you're given a table. And remember, you're never going to memorize these things, but you can you use these equivalent values here. The 8 pounds doesn't need any conversion to get to nitrogen, but here's a conversion of P2O5 or K2O, how you get to different things. And again, a special blend of fertilizers, it's like a cocktail that some fertilizer company may make up, may not say anything like potassium nitrate. They just may leave it as 821-4 or something like that. But nevertheless, you can determine what the basic constituents are. This gives you an idea. It's relatively old, but it's a table that nevertheless gives you an idea what's going on. These numbers change all the time. But this table 11.1 provides grades and usage of fertilizers some time ago. If you look at the second item down there in the table, it says identified by grade. That means it's something like just some numbers. It doesn't say exactly what they are, and that's the big gorilla. If you kind of scan down there, you see numbers of, let's see, that's 2 million, and then there's anhydrous ammonia, that's 170,000. That's a pretty big number. And then you have other numbers that are kind of small, like ammonium nitrate. That's not a big number there. And then you have ammonium nitrate solution. Okay, what that means is some of this stuff is solids and some of it's liquid. And I've mentioned before, and this shows that most of the fertilizers we use in California are liquid. And then you go down and you find all sorts of other chemicals. But there are some big numbers and some small numbers, but it gives you a little idea of the mix and the different grades that are out there. Again, to reiterate, most of our fertilizers for many years here in the United States are liquid, and therefore it's really easy to fertigate. So you find these tanks, and they're filled up by the fertilizer companies. The fertilizer companies bring in a liquid fertilizer. And this is pretty typical in the United States. We have tanks sitting out there that are refilled by fertilizer companies, and they're all injected at one central location. Now, granted, there are mobile systems, but this is generally the idea. In other countries, quite often you find solid fertilizers for the simple reason that the roads may not be quite so good, the transportation isn't so great, and so if you're transporting water, paying for that, you're paying a lot of extra. So what they do is they transport the fertilizers in a solid form, and then they mix it at the farm, not usually at the field, but at the farm. And you have two pictures here, one on the left, one kind of on the upper side. The one on the left shows a tank that's easy to fill because the top of the tank is about ground level. And then there's a pump down below. But as you can imagine, whenever there's a leak, this gets kind of gnarly in terms of trying to repair everything. So that's generally not recommended. What you really ought to have is everything above ground, which you sort of see on the right. What you see there is also a ramp that they can take wheelbarrows and so on and move up and then dump the fertilizer in. And of course you can get a lot more sophisticated than this. But this happens to be for a very large installation. So again, to reiterate, everything should be above ground. Some have flooding problems. Always think about how easy it is to fill tanks with solids. Sometimes I see some of these, and the guys are putting in bag by bag. That's granted, labor is less expensive in some other countries, but not that inexpensive. You may as well think it out in terms of how guys can get the chemical in. And then how do you mix the chemical with the water? There are basically three ways that people do it. They use air sometimes because the bubbling mixes everything up. Or they recirculate the solution with a pump, and or they have a mechanical mixer like a propeller that extends down into the tank. But one of the biggest problems that people have is that they just try to dissolve too much at once, and there's a solubility limit for every one of these chemicals, and that also depends on the temperature, of course. Here in the USA, when we have solids that we mix, we typically do it at the field near the pumps, and so you have a variety of commercial mixing units. The one on the upper right has some mechanical means, for example, and then there's the one in the center is part of a gypsum mixing unit. But really, probably the two biggest chemicals that I see that come as solids and need to be mixed are potassium sulfate. That's often an inexpensive source of potassium, and gypsum. There's a big difference in the solubility of these two, though. Gypsum has very limited solubility, and potassium sulfate is much more soluble. That brings up a real important point for drip irrigation and for sprinkler irrigation. There are three different terms people use, and they get them intermixed sometimes. There's a slurry, and then there's a suspension, and then a solution. Now, if you look at the blue part of this, it says for most fertigation, you really need a solution. That means everything is dissolved. In other words, the chemical, like let's say gypsum, which is calcium sulfate with some water molecules attached, it'll split up into calcium and sulfate. It won't exist in the water as calcium sulfate. In other words, as a little piece of rock. And again, it has limits on solubility. A slurry or suspension is something where you have the chemical, the solid particles, and they're floating along in the water. They're moving right along, but they haven't dissolved. And so they're small solid particles. Especially with gypsum, you see a lot of farmers with microsprayers where the microsprayers can get worn out, the nozzles get worn out within a year because the gypsum wasn't adequately dissolved. They have too high application rate. And it isn't that it plugs the sprinklers, but it wears them out, and so you get non-uniformity because you get, big nozzles and small nozzles out there. On emitters, they tend to plug emitters, so there's a different kind of a problem. In general, the safe rule is to always inject upstream of drip and microfilters. And then the idea is you would catch things. People don't like it because then the filters plug up. Get that. Actually, what they should do is be thankful that the filters are plugging up instead of their drip system. But hey, that's the way it goes. So, one way guys sometimes eliminate problems is they just inject downstream. And all it is they don't see the problem. The emitters are plugging up, but they don't notice it right away. And you can't really clean up plugged emitters. That gets really, really tough to do. You end up with high chemical rates, like really dropping the acid low, and then you sort of fry your roots, and it's not a very good deal at all. So what you ought to have here is in the injection upstream. Now in this particular picture, if you notice, the water's coming out of the filters on the lower pipe. That's the way these media filters work. And all the injection ports are downstream then of the filter. They do have one thing right. They have their flow meter. It looks like a little magnetic flow meter. There, it's upstream of the injection ports and it's downstream of the filter, so it certainly isn't going to get plugged up. But although magnetic meters don't get plugged up, so they have some of the ideas right, but they're injecting downstream of the filter. So again, if you put something like gypsum in downstream of the filters, you're really looking for trouble. Now, we have this slide in here just to show you that there are things that are done differently in other countries. This is a photo from a large farm with sugarcane in Peru, and it's a very modern one. They have center pivots. And they have a centralized mixing plant, in the kind of the middle of the farm. And then they put the mixed fertilizer, in other words, the solutions, in these tanks right here. And then what in the world are all these things? These are pumps, and different pumps. They're chemical pumps now. They're not water pumps. They're chemical pumps. So, you have to have stainless steel and all that. And if you notice, they have lots of little pipes going out. So believe it or not, they'll have miles and miles of these pipes, these polyethylene pipes going out, just with fertilizer. And that's it. And these pop up at every center pivot point. And then they have an injection system at each center pivot, which will take this fertilizer from one or more of the pipes that pop up there and will inject it at the correct rate. And they may pressurize it, or these pumps can provide enough pressure so they don't even have to pressurize the fertilizer. Basically what they're doing is injecting it at the appropriate rate. In other words, what they have is they don't have tanks out in the field. They have outlets, kind of like turnouts at each field, for water and for each of the types of fertilizers that they have. And again, this is not common in the United States yet. I've mentioned the idea that different fertilizers have different solubilities, and it's a function of the temperature. And so this is a table that gives you an idea. You can look at the numbers they're in your book. But you see that each chemical is different. So the solubility, for example, of the second one down, ammonium nitrate, you look at the numbers, and the 9.9, 12.6, 16.0, those are big numbers. And then you go down to potassium sulfate, and the numbers are 0.7, 0.8, 0.9, so they're less than 10% of ammonium nitrate. So it just means you can only mix a certain amount before it starts precipitating out. We have a whole video just showing lab results, examples of mixing different fertilizers together. But there are two types of incompatibility, you might remember. One is different fertilizers that are mixed together, and that's what we show you in this other video. And then there are also incompatibilities with the irrigation water. And so what happens then? Well, obviously if the fertilizers mix together and fall out, they don't do you much good. But also then that precipitate can plug nozzles and emitters, and sometimes you can't dissolve that stuff, like phosphorus compounds. It just doesn't work. Then there's volatilization of nitrogen as ammonia gas. In other words, it's NH3. It just poof goes right into the air instead of going out in your field. It'll even burn the leaves on crops. You'll see that sometimes, where especially with furrow irrigation at the beginning of a field, you'll see some of the leaves are burned because of ammonia gas that's escaping into the air. And then the injectors and tanks can be plugged also. So it's something to pay a little bit of attention to. Here's an example of one tank, just as an example here. And the rule, of course, is don't mix different chemicals in the same tank. People just don't keep track of what they're doing. In other words, use a lot of tanks and a lot of different injectors. This photo here on the top, you can see that at different dates they put in different fertilizers. And then, I took a look at the inside of a tank, and it's a little difficult to see here, these circles and that, but basically the bottom of the tank is packed solid with solid something, where fertilizer's mixed, and they precipitate it out. So it's didn't do much good there. Remember, the idea is it's a good idea to conduct a jar test before injecting chemicals. It's a hassle to do it. People don't do it. And then sometimes, occasionally you see disastrous results. But anyway, the idea is you mix the irrigation water and chemical in the same proportions that you expect during fertigation. It turns out if you really stick a lot of chemical in the irrigation water, sometimes it overloads the system and you don't see the problem. But you let the jar sit overnight, and if there's cloudiness or precipitation, there may be a problem with compatibility. Again, to repeat, there's a different video in this series that illustrates these ideas: volatilization of ammonia and incompatibility. And now, how's this for a lousy looking canal? It's a slip-form concrete canal with all this, whatever it is on the sides, And this is something I've noticed over the years. I go to different places, and you can tell this is down in either northern Mexico, northwestern Mexico, or down in Arizona, New Mexico. That's where you typically see it, where a lot of people use anhydrous ammonia or aqua ammonia for fertigation. And so what in the world are you looking at here? What it is they have hard water. Hard water is water with a large amount of calcium and magnesium in it. And that's just the kind of water they have from wells or from their surface water supplies. So that means a lot of calcium and magnesium. And this is what happens when they put anhydrous and aqua ammonia. So what in the world is it? First of all, that's not the fertilizer that you see. Instead, it's stuff that came out of the water. How's that? It's the calcium that was in the water that dropped out. There's even an old University of California publication, believe it or not, that has some recommendations on how to seal leaky concrete pipe. And what the recommendation is to inject anhydrous ammonia into water into these old concrete pipes. Calcium drops out, basically makes concrete, and then seals the holes. At least that's the way it's supposed to work. And there's a little equation on the bottom left here that shows what goes on when you put ammonia, that's NH3, into the water. it'll convert to ammonium plus an OH ion. And then the OH ion then is in the water, and when it combines with the calcium that's in the water, it drops out as lime, or a precipitate. And that's really what you see here on the banks of the canal, is the lime. Now, these reactions get a little wild, because then you know it's an equilibrium reaction, and when you have a high pH, it shifts things back to the NH3, and on top of this problem right here, you also get a fair amount of the ammonia that just volatilizes. The bottom line is, if you have real hard water, anhydrous ammonia and aqua ammonia are not the greatest selections for fertilizer. This shows the other half that I mentioned, the problem with the volatilization of ammonia, and how there's an equilibrium reaction between ammonia and ammonium. And the photo itself shows you what these tanks look like. You know, you have the ammonia gas, and it's under pressure, and there's a hose going down into an irrigation district turnout. This is an irrigation district, gets water out of the Colorado River. And anyway, they're injecting the ammonia, and then it converts with the water into ammonium and hydroxide, but then if it's high pH, it doesn't all convert, and so you get volatilization. With phosphorus fertigation, the bad news is that phosphate combines with all kinds of things, iron, magnesium, and you've seen images of this before. And essentially, if the phosphate precipitates out, it's unavailable and it plugs emitters. Those are two bad things. Good news is that there are fertilizers that can overcome that problem. But with phosphorus, you always do want to do jar tests just to make sure, kind of double check things. And then, and by the way, there are other things that happen too. You know, sometimes, in one case I remember looking at a huge system, drip system, and it was just about completely plugged. They were injecting the right fertilizers, except what happened is the fertilizer company, for some reason, delivered the wrong fertilizer. And of course, you know, you just inject it because you think you have the right thing. There were no jar tests done, and it was a disaster on a really large field. You know, problems happen. Anyway, there in the book, we have a description of various things: MAP, some monoammonium phosphate, and then there's MKP and urea phosphate and phosphoric acid. There are a number of acidic fertilizers that have been quite successfully used to inject phosphorus. So you can check with your fertilizer dealer, find out what they have. I recommend doing a jar test anyway, and read up on it in the book, and you'll be able to move ahead. Figure 11.8, I think, is an interesting image. It's provided by Netafim. You know, they're one of the major drip micro irrigation manufacturers, and they have a book which is quite helpful in terms of guiding people on fertigation. And what they have here listed is they have common nitrogen fertilizers that are used, common potassium fertilizers that are used, and then phosphorus fertilizers that are used. And then also there's NPK mixes, and then micronutrients. So again, that's figure 11.8 you'll find in the book. So let's see, a lot of the fertilizers actually are acidic, or they end up acidifying the soil. And I've mentioned before that it's real easy to acidify a soil. It's really difficult to bring the pH back up. Some of our soils in the western US at least have large amounts of free lime, and so you could be injecting acidic fertilizers for generations and really have no effect. But that's quite often not the case. And what happens, as you've seen before, is if you drop the pH too much, then micronutrients become unavailable, or they become toxic, and regular nutrients, you know, they're not as available. And basically, you like to keep your pH, you know, somewhere close to neutral. And So you can do things if you have row crops. For example, this is a picture of a large applicator of lime, and you can spread this stuff out and mix it in the soil, and that's pretty easy. So how do you get the lime in the soil to react with the hydrogen ions to raise the pH if it's acidic? Now that's a tough one, because lime is insoluble. So let's see, you can't really inject it through the irrigation system. You'll just plug the emitters or ruin your microsprayers. So here's what we do. If you notice, item number 1 deals with gypsum. We have 2 ways of putting gypsum on. One is we inject it through the irrigation system, and we have a whole section on that. It has to be very finely ground, high purity gypsum. Or we actually cover the soil surface that's going to be wet with gypsum. And here's the idea. It's very different from what you read in soil science books. While the gypsum, which is calcium sulfate, the gypsum does not react with hydrogen ions to create water. What you do with the calcium that's in the gypsum is when it gets down there, it overrides the hydrogen that's on the exchange sites. In other words, it'll bump them off, and then the hydrogen actually gets leached down. Kind of an unusual thing, but that's the way it goes. The other is, instead of applying gypsum to the soil surface, you can apply real ground, finely ground, highly pure lime to the soil under the emitters, and then when the acidic water, if that's the problem, if there's acidic water arrives, it gets neutralized. Most people use the gypsum. So this is the end of video number 7, and we welcome you to check your website and YouTube and get video number 8. Thank you. Goodbye.